if you want to jump in and ask a question, please please feel free to. Okay, I'm recording. Let's share the screen. Okay, so this is some Math 9 stuff. Let's go away from that. Okay. 12. Okay, and then okay, so balancing. Okay, so so let's start with maybe like an easier question first, and I'll try to post the video I did in class yesterday. It's a little experiment we did with some of the students that were there, and just talked about balancing. Oh, also I was going to say sometimes my audio craps out on me and it gets all staticky. If that happens, if one of you guys could just say something like say, hey, your video's out, and that's actually usually enough to fix the video if someone just says something and my computer goes back to normal for some weird reason. But let me know, because I know it's no fun hearing that. So in class yesterday, what we did was we had a beaker, and we put in a solution that had a copper 2+ in it, and sorry, no, sorry, that's wrong. Sorry, we had silver ions in it, and we put in a bar of copper metal, and we also put some copper beads in also, but basically putting some copper into some silver ion solution. And so before I start balancing it here, what I want to do is a quick review of some of the stuff you guys did on the previous quiz, which it looks like most of you guys really know quite well, like oxidizing agents, reducing agents. But I would like you to do is predict whether a reaction would take place or not, and if so, what would the products be here. So if you could just take a second to use your data table just to make a prediction of what you think would happen here. And then we'll talk about the balancing aspect of that. And I have to find my book, so I'll be leaving the room just for a second. So, but I will be back. And Glenn, I'm not sure if you can hear me still, but are you, when are you leaving for work?
Probably in like 20, 25 minutes.
Okay. If I'm done by then, I'll chat with you on the video here, but if not, I'll send you an email, okay?
All right, but like, did I submit something to you?
No.
No? Okay, well, I did it, and I have them all written down somewhere. I just
Okay,
must not hit submit. I was in a rush to get to work when I was doing it.
okay, well, let me talk to you about that privately, if that's okay.
Yeah, of course.
Okay. Okay, so if you have your data table in front of you, I'm not going to switch back and forth here because I know that can be a bit distracting, and I'm sure you guys can see this. But what I've been encouraging you guys to do on previous videos is just to make a little column or make a note of what could get reduced and what could get oxidized here. So silver ions, they can definitely be reduced to silver metal. So I'm pretty sure they're going to be on the reduction side of the table, and that means they're actually acting as oxidizing agents. And I know copper metal, I know almost all metals can be oxidized, so copper metal should be able to be oxidized. But really what we want to do is predict whether this would even occur in the first place. So I need to know sort of the positional place of these items. So the silver, if you're looking for silver, it's at 0.8 on the data table. And if you're looking for copper, it actually appears twice at 252 and 34, I think. So you get copper metal and copper metal. And the way I've written this is actually how it appears on the table, and that is to say that the silver reaction is higher than the copper reaction. So in previous videos, I called this a step down reaction. So that means that the it's not nothing to do with gender there, but it's going downhill, and it's a spontaneous reaction then. So oh, any chance here? Hi, Amanda. We're kind of doing a similar question we did in class yesterday, and so you haven't missed too much of that. So okay, so we have things can get reduced, things can get oxidized. So the silver is going to get reduced, and the copper is going to get oxidized. But the silver ions, the only thing that can really happen to them is turn into silver metal, and that would have to be one electron to do that. And the copper, though, it actually shows two different reactions that could take place. The 5-2 reaction shows copper 1+ being produced, and that would produce one electron. And then the copper metal could also get oxidized to form copper 2+, and it would make 2 electrons there. So basically, I know for sure that the silver ions are going to turn into silver metal. But what I don't know, or at least I sort of I'm unclear of maybe what happens with the copper. Like, does the copper get turned into Cu1+, or does it get turned into Cu2+? And so this is where the data table shows that the further down on the right-hand side you go, the stronger of a reducing agent you are, which means the more likely you are to get oxidized. So when you have more than one item on one side of the table, you always pick the one that's lowest down on the right-hand side, which means the 3-4 reaction is what's going to take place. So you're going to get copper 2+ forming in your reaction here. And once again, if I'm talking too quickly or you have questions, please jump in. Okay, let's look at some in the chat here. So sorry. Yeah. Okay. Anyway, there we go. So let me go back there. So I'm all befuddled now. So here we go. So we got copper 2+ forming in our reaction. Now, if you look at this reaction the way I've written it, I think for a lot of students, if you were to say, chemistry 11 going to chemistry 12, that looks pretty balanced. I mean, you've got one copper. Oh, what's going on here? What did I do? Oh, hey, Bardia. Okay, just going to ask, make sure your cameras are off, just so I don't have if filming your faces. So this reaction looks fairly balanced. I've got one silver ion, one copper metal, one silver atom, and one copper ion here. But in terms of balancing, it doesn't just have to be balanced for the number of particles. It also has to be balanced for charge here. And if you look at the reaction, this might make a bit more sense why. The silver reaction, it requires one electron in order to reduce the ion into silver metal. But what's interesting is the copper metal actually produces 2 electrons. So it would like produce these 2 electrons, and those 2 electrons would have to go somewhere. They would be being taken by something, which is the oxidizing agent. And so in this reaction, which chemical actually is the oxidizing agent? Like which chemical in the process is the thing that's causing the oxidation of another chemical? Well, the copper is being oxidized, so the silver ions, they are the oxidizing agents, and the copper is the reducing agent. So don't forget that the silver is taking electrons and the copper is giving the electrons. That's where it's giving them. And the whole reason the copper gives the electrons in the first place is because the silver is taking them. So what actually has to happen here is the number of electrons number of electrons used will always equal the number of electrons lost. So here we have kind of an imbalance. The copper produces 2 electrons, but the silver takes 1 electron. So we look for the lowest common multiple of these numbers, which is 2. And that means that the silver would take 2 electrons, but we need to have 2 silver ions to do that, which would make 2 silver atoms. So to balance this reaction, we have to have a 2 and a 2 here. So there's never electrons left over in a redox reaction here. So that's a fairly easy one to balance, because you could just think about the charge even, just say, well, I need to have a +2 on both sides. So let's put a 2 in front of the silver, and now I need to balance the silver, so we'll put a 2 in front of the silver metal on the right-hand side. So that kind of question is a fairly straightforward one to balance, and there's no really fancy tricks you have to do that. But in yesterday's class, I did cover a method called the major hydroxide method. And I actually prefer to write it this way, major hydroxide method. This is just a memory device for you, kind of like an Leo goes Gur. But the major part here is what you should always start with. So we balance what are called major species first. And that basically means no oxygen or hydrogen. So you would basically ignore the oxygens and hydrogens in the reaction, if there are any. The second thing you want to balance is balance oxygen. And we do that by adding water. And the third thing we balance are hydrogens. And we do that by adding protons. And then the fourth thing we balance is charge. And we do that by adding electrons to the reaction itself. And what I'm going to focus on first of all is balancing a half cell. So we're going to balance a half cell. And so once again, a half cell is part of the redox reaction. So it's either the reduction part or it's the oxidation part. So it'd be kind of like me balancing, I'm just going to circle it here. Let's use blue here. It'd be like me balancing just that part, or balancing just this part, not balancing the entire reaction yet. I think that's too much to do in one big step here. So I'm going to balance a redox reaction, a half cell reaction, and let me just pick one that's easy. I think I'll probably pick one I did yesterday. Yeah, I'll do two that I would have done yesterday. So let's take a look at this reaction. So let's say you had the reaction RuO2. See? RuO2, and it was turning into Ru. And so this is a half cell. And what I mean by that is this is not a full redox reaction. This particular reaction either shows reduction or oxidation. And if you know the major hydroxide method, the benefit of knowing this method is you don't even have to understand what's being reduced and what's being oxidized. This method will just balance the equation, and you don't even have to predict what's being reduced and oxidized here. But let's just show you how you would know what's going on here with this. So here the Ru has an oxidation number equal to 0. And over here, this oxidation of the Ru would be X minus the 4 for the oxygen equaling 0. So the oxidation number here is equal to 4. So we're going from 4 to 0, and so that's definitely reduction going on. So I'm thinking there's got to be like electrons being added here at some point. But let's use this major hydroxide method and show you how you balance it. It's basically an algorithm on how to balance them, and it's not based on chemistry. It's just based on mathematics in terms of how to get to the right answer here. So let's start off with our major species. So the major species is any chemical that is not oxygen or hydrogen. So in this case, the Ru. So I've got one Ru on the left side, and I've got one Ru on the right side. So my step one is balanced. So my major species are balanced. So now I go to balance out the oxygens, and I notice there's 2 oxygen on the left and no oxygen on the right. So I need to add some oxygens here. But in order to do that, I use water here to be the oxygens. So I need to have 2 oxygens, so I add 2 waters to that side. And then now I've just introduced a bunch of hydrogen here, so I got to take care of the hydrogens. And I've added 2 waters, so I've introduced 4 hydrogens. So I'm going to add 4H plus. So I have 4H pluses here. And now I've balanced my major species, I've balanced my oxygen, I've balanced my hydrogen. Now I need to balance charge by adding electrons. Now notice that the right-hand side has no charge. This charge of, I'll use a different color here, charge of 0 on the side here. See? Just accepting people here. And then on the left-hand side, I have a charge of +4 because of the 4 hydrogens I added. So I need to add a certain number of electrons to make the charges balance on both sides. Now, when you add electrons, you got to remember that when you add electrons, the charge is going to go down because the electrons are negative. So if I was to add electrons to the right-hand side, it would become more negative. And if I add electrons to the left-hand side, it becomes more negative. So on the right-hand side, I have a 0 charge, and on the left-hand side, I have a +4. So I'm going to add electrons in a way that causes, so make sure someone's not waiting here. There we go. I'm going to add electrons to the side that has the larger charge because I want to bring that charge down. So I'm going to add 4 electrons here. And that now makes both sides have a net charge of 0. Now, if you count all the chemicals in that reaction, they're all balanced now. The RUs are balanced, the O's are balanced, the H's are balanced, and the charge is balanced. And so for you to guess that, like you just sort of on your own guess that that's what the reaction is, I think that's pretty hard to do. So I think learning the major hydroxide method is quite handy. So let's try another one. I'm going to give you guys just a little bit of time to try it on your own, and I will answer it for you, but just to give you some time to answer it here. So let's do where is it here? Yeah, that looks pretty fun. Let's go H3 ASO4 turning into HASO2. I'm just gonna double check. There's a comment here, but just give me 1 sec. H3ASO4 going to HASO2. Sorry, comment. Sorry. I appreciate the comedy. Okay, so here we go. So why don't you guys try that and just see where you get to with that, because it's tricky. This is a tricky thing. Okay, major species is AS here, so it looks like I have 1 on either side, so that's pretty hunky-dory. And then I need to balance my hydrogens. I've got 3 on the left, 1 on the right. So I need, balance my oxygens. I got 4 on the left, 2 on the right. So I'm going to add 2 waters. So let's add 2 waters here. So 2 H2O. And now I have 3 hydrogens on the left, and I have 3 hydrogens on the left and 5 hydrogens on the right, because there's 4 from the water and 1 from the original compound. So I've got 3 H's and 5 H's. So I need to have 2 more H's on the left. So I'm going to add 2 H plus. So 2 H plus. And now I need to balance out my charge. So I'm going to add 2 electrons to the left. I'm just going to double check if I did that right. So 1 AS, 4 oxygens, yeah. 5 hydrogens, and charge is that. Now notice that you added electrons here, so that means that this reaction would have been reduction, but you'll notice I never even determined that. Like I never even determined, is it a reduction or oxidation reaction here? But if you actually work it out, you'll see it is reduction, because you've got 3 from the hydrogens plus the AS, which is X, minus the 4, or minus the 8 actually, equals 0. So the X here would be, would that be -5, so 5. And on the other side, you have 1 plus X minus 4 equals 0. So here you have the oxidation number equaling 3. So it is actually also a reduction reaction. And you'll also notice that it's a reduction of charge of 2. And notice you have 2 electrons here, whereas above it went from 4 to 0, and you had 4 electrons here. So there is sort of a justification of why the electrons are are what you see here. But the major hydroxide method is just a really fast, or relatively fast method to predict these things. So I want to do one more example, and I'm not going to have you guys work through it. I'm just going to do it for you, but just to show you some of those things. Yeah, so in the last example there, the 2 electrons I added are because the hydrogens I added changed the charge on the left-hand side of the equation. So in the beginning, it looked like both sides had the same charge, but as soon as I introduced the hydrogen ions, I have to account for that charge. Is that okay, Noah? Okay, so yep, okay. So I'm just going to go on with a slightly different question, just sort of show you where you do have to be a little bit careful about subscripts. So CR2O7, 2 minus, turning into CR3 plus. Okay, so here's a situation where you'll notice that the major species isn't balanced, and if you missed it, like if you missed that, you could probably see how easily you could go wrong after that. Like for example, you might say, oh, let's balance out the oxygens by adding 7 waters, but you have to balance the major species first. So I need to put a 2 in front of that chromium, and then now I need to balance out the oxygens. So in this case here, this definitely would still be a 1 on that side. So I do need 7 H2Os. So that wouldn't have caused a mistake yet. And now you might say, well, I got 14 hydrogens on the right, so I'm going to need to have 14 hydrogens on this side. But now where the problem would be is calculating how many electrons you need. If you didn't put that 2 in there, you're going to make a mistake with the overall charge here. So on the right-hand side, it's +6, because you have 2 chromium, 3 pluses. And on the left-hand side, you got 14 because of the hydrogens, but then you have to -2 because of the CR2O7. So you actually have +12 on the left-hand side. So I need to add 6 electrons here to balance things out. So I'm going to add 6 electrons to the more positive side. So once again, this would have also been a reduction reaction. Okay, so that's how you balance a half cell. So these are all half cells. And what I'm going to do is I'm going to balance the reaction we did at the very beginning. Now, if you missed that, I'm just going to scroll up here. And I'm going to rewrite this for you guys if you didn't have that written. But let's balance this using the major hydroxide method, and sort of show why it would be kind of ridiculous to do that. But let's just go down here and let's just say you wrote this. So let's call it balancing a full redox reaction. Okay, so you're going to balance a full redox reaction here. And let's say you're told that you have Ag plus copper forms into Ag plus copper 2 plus. Now, we already know the answer to this question, but just to sort of show the mechanics of this with an easier question, because the harder ones do get much more challenging, is let's say we break it apart first of all. So what we kind of want to do is look at one of the cells, one of the half cells. So I'll call this cell 1, and let's call this cell 2. Okay. And once again, I wouldn't do it for this particular reaction because this one's really easy to balance. But what I do is I just pick one of the reactants on the left-hand side. So let's say Ag plus, and I'm going to say that this would be a half cell, in that it's either reduction or oxidation. And I'm going to make a prediction what the products would be here. So I know that my choices are pretty limited here. Like I've got these as the reactants, and I've got these as the products. So basically, the reactants have to turn into products. That's the whole idea of chemistry. And so if you said, well, maybe it does that. Well, you're probably really high right now, right? You might have had like a big party or something like that, because that would be ridiculous, right? Because that's like alchemy, right? So if you have a chemical that's silver, it's an ion, and it's turning into something, it still has to be silver. This is not nuclear chemistry, so we're looking at sort of physical chemistry. So the silver ions would have to turn into something that has silver. And we can see from the reaction, the only thing that has silver is silver. So it's just Ag. And then I look at the other half cell and I think, okay, well, copper metal, it's got to be turning into something. What would it most likely turn into? Well, most likely it would turn into a copper compound, in this case, Cu2+. Okay, so now I've determined my two half cells, and once again, I'm not even going to predict what's reduction and what's oxidation, although it's kind of obvious here. But what I do now is I just balance these half cells just the way we did before, using the major hydroxide method. So major means major species. So in this case, silver. So silver is already balanced because you got 1 and 1. Then you balance out the oxygens, which there are none, so you can leave that out. You then balance out the hydrogens, which there are none, so you can leave that out. And then finally, you balance the charge. And to balance the charge, you'd have to add 1 electron to the left-hand side. And so you add 1 electron. Okay, and that's the half cell for silver balanced. The copper reaction, you have same basic things. You got 1 and 1 copper, no oxygen, no hydrogen, but you do have an imbalance of charge. So I'd have to add 2 electrons to the right-hand side. So that half cell is balanced. Now remember, this is a full redox reaction. So something's getting reduced and something's getting oxidized. So clearly the silver is getting reduced and the copper is being oxidized. But now we've got to put it together to a final reaction. So what we have to look for is the concept that, and I wrote this above, is that the, let me just, I'll use a fancy color. My daughter was drawing on this yesterday, so this is a fancy color here for us here. Let's say number of electrons gained will always equal number of electrons lost in a full redox reaction. Okay, so that's really important to our next step, which will actually be a new step for us. We haven't done this part yet. Okay, so what we have to realize is the copper is producing 2 electrons. The silver is needing 1 electron. So the lowest common multiple of those would be 2. So right now my copper reaction is fine, but I'm going to times the silver reaction by 2, and kind of like a math problem, I'm going to write it underneath here. So I'm going to say that would be 2 electrons plus 2 silver ions going to form 2 silver metal atoms. And then what we do is we add the 2 half cells together. And what's always going to happen here, or what should always happen here, is the electron should always cancel. Because remember, the electrons produced equal electrons gained. So these 2 electrons cancel. And now we get copper plus 2 silver ions going to form copper ion plus 2 silver metal. Now, admittedly, that is overkill for that reaction because you could easily just sort of see the ratio here. But let's give you a question where that would not be maybe as easy as this particular one. So here we go. Let's take a look at let's see here. That's a good one. Okay, so let's say you have oh, sorry, question. Yeah, I'll still have to talk to you privately about that, Glenn. Okay, because I can't accept that right now. Okay, sorry, but I'll talk to you later about that. Okay, so I'll send you an email out today. Okay, so we're gonna take a look at osmium plus IO3 minus going to form OSO4 plus I2. Okay, so this is a bit more complicated looking. And so we're being asked to balance this reaction, balance this full reaction here. To do that, I need to be kind of careful here what I'm grouping my terms here. So one of my cells, let's call it cell 1, would have to be, well, it would have to be, but let's just pick OS as an example. Maybe I'll leave a little bit of space, or sometimes it's write stuff on the left-hand side. So let's write OS. Turning into some product, okay? Now, the 2 products I have are OSO4 and IO2. And so I'm thinking that osmium must be turned into something that has OS in it. So I'm going to pick OSO4. because you kind of have to have the same major species being produced here. Now in cell number 2, that must be something to do with the iodine. So I'll take the IO3 minus and have that turn into I2. Okay, now what I do here is I separate the two cells and just work with them separately and not try to combine them right now. And so I'm going to try to balance the major species first. So OS is already balanced. But the oxygens, there's 4 oxygens on the right-hand side, but none on the left-hand side. So I'm going to add 4 waters. Okay, so that's done. But now I've introduced 8 hydrogens, so I'm going to have to add 8 hydrogens. Okay, and now the left-hand side has no net charge, but the right-hand side has a +8 charge. So I need to have to add 8 electrons here. And I'm just double checking one OS. Oh, sorry, I wrote that weird over here, sorry. 4 water, sorry. Okay, and now I got to balance the other half. So now I've kind of gotten pretty squished up here. So I'm going to just draw a line down the side here so I don't confuse these things. And I'm going to write IO3, sorry, here. And that's turning into turning into I2 here. So first thing is major species. So I have 2 I's on the right-hand side, so I'm going to need to have 2 here. I've now made 6 oxygens instead of 3, so 6 now. So I need 6 waters. Okay, and now I've introduced 12 hydrogens. So let me just get rid of this bar here. Just draw it like that. There we go. So I've added 6 oxygens on both sides, but 12 hydrogens. So I need to have 12 H pluses. And now I got to deal with charge. I'll be a bit careful here. The right-hand side has no charge, but the left-hand side has +12 from the hydrogen, but then -2 for the 2 IO3s. So right now, the left-hand side has a +10 charge, and the right-hand side has a 0 charge. So I need to have 10 electrons being added here. So let me just check that. Yeah, 10 electrons plus 10. Okay, so these 2 half cells are now balanced, but notice that was going to be a fun one, that the left-hand side reaction produces 8 electrons and the right-hand side needs 10 electrons. So what is the lowest common multiple of 8 and 10? So I mean, you might think 80, but I'm thinking a bit smaller here, so maybe 40. So I could times the top equation. I need to make 40 electrons here. So I could times this one by 5. So that's going to give me, there's going to be a lot of math here. 5 times 4 is 20 H2O plus 5 OS, going to form 5 OSO4 plus 40 H pluses plus 40 electrons. Okay. And then this reaction, I'm going to times that one by 4, because I need to get 40 electrons here. So times it by 4, 4 times 10 would be 40 electrons, plus 4 times 12 would be 48 H pluses, plus 2 times 4 is 8 IO3 minus, going to form 4 I2 plus 4 times 6 is 24 waters. Ay, 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 ay. Okay, now this is the last step here. What has to happen here, if you've done it right, is the electrons have to cancel. Electrons produced have to equal electrons lost, okay? Sorry, electrons produced equal electrons gained. So now what I do is I cancel out the things that are on both left and right side if I can cancel them out. So for example, the top equation produces 40 electrons, but the bottom equation uses 40 electrons. So they're gone, okay? Now, also notice you have H pluses on both sides. So this side has 40 H pluses, whereas this side has 8 H pluses. So you make 40, but you use 48. So use 40, gone. Use 40, so 8 left. So you have 8 H pluses left. You also have water on both sides. So you have water here, and you have water here. So the top one needs 20 waters. The bottom one produces 24 waters. So you use 20 but make 24. So really you have a net production of 4 here. So cancel that, and you get 4. And I think that's everything that's on both sides of the equation. So let's just write that down. So now I have no waters on the left. So I have 5 OS plus 8 H plus 8 IO3. And notice I've used everything to the left of the yield sign. Okay, so I've just taken all the reactants. And now that's going to form, I might want to make this not look like 81, but I think your teacher would understand. I know what you're doing. And that's going to form 5OSO4 plus 4I2 plus 4H2O. And if you count things, you got 5 OSs on both sides. You've got 8 iodines on both sides. You got 24 oxygens on both sides. Yep. You've got 8 hydrogens on both sides. Left-hand side has a net charge of 0, and so does the right-hand side. So everything's all balanced there. But you know how you would come up with that just guessing? I don't know. You'd be a pretty lucky person if you could guess that. Now, for those of you, I know there's some of you guys on here like are super keen math students. There is a method called balancing by oxidation, which you might want to look at. It actually takes fewer steps, but there's a lot more math involved. So, and it doesn't work for every question. There's a few questions that this method will work for, whereas the other method doesn't always work for. So I would encourage you to learn this method. So I'm just looking at the time here. I wanted to do one more question, and it's a question that I posed to the class yesterday and said I would look at, was how do we balance in basic conditions? How do we balance in basic conditions? And what I mean by that is if you look at the reaction we just balanced, like the ones we just did here, that actually would be classified as balancing it under what we call acidic conditions. And that means that this reaction you're looking at, the one we just balanced, that if you had this happening in a glass of water, it wouldn't happen. It just wouldn't happen the way it is. And you might say, well, how do you know that? If you look at the second compound I have written here, it says 8 H pluses. And that implies that you have protons, which really would be hydronium, of course, free floating in the water, which means the pH of this would be well below 7. And if you actually look at the data table on the redox reactions, there's actually quite a few reactions that you'll see like this that have these H pluses. And that means they're taking place in acidic conditions. So if you were taking place in basic conditions, then you wouldn't want to be looking for H pluses. You'd want to be looking for OH minuses. So this reaction that we just balanced, you can balance that under acidic. You can't actually balance it under neutral conditions, but you can balance it under basic conditions. I'm going to show you how to do it really quickly here. So what I would say, first of all, is use all the things we've taught you and get down to what we have right here, the reaction under acidic conditions. And then what you want to do is use one last step to convert to basic conditions. And what you're going to use is, you might remember in the acid-base chapter, the self-ionization of water, which was 2H2O, equilibrium hydronium plus hydroxide. But what I'm going to write out is just H2O, equilibrium H plus, and hydroxide. Now we know that it's really the first one, that's really what's going on, but because this reaction uses H plus, I'm going to use the bottom reaction here. And sometimes you might have to write the reverse of this, and I'll talk about why in a second here, that reaction. So I'm going to focus on this one or that one there, okay? So what I want to do now is I want to get rid of my H pluses, and I want to introduce hydroxide. So below this reaction right here, I'm going to write the water reaction, but I have to choose, do I want the first one or the second one? So what I want to have happen is I want the hydrogens to cancel. So I have right now hydrogens on the left, so I want hydrogens on the right-hand side. So I'm going to write the first reaction here, which should have been a minus there, and an H2O. Now the problem is I only have one H written right now, so I really want to have 8 H's here to cancel out the 8 H's on the other side. So I'm going to times the water reaction by 8. Now I should just clarify this for the students that are like, why is he doing this? This is not really a chemistry reason why we do this. It's more of an algorithm that works. So it gives us the right answer here. So you'll see that it will be balanced afterwards. So what I'm going to do is use the water reaction. And now what I notice is the H pluses are gone. They're going to cancel from the equation. Now I do have to take care of some water here because the right-hand side had 4 waters. This had 8 waters. So really I have 4 waters left. So maybe I should have just canceled the number maybe. So 4 H's left. So now I balance this reaction. So I get 5 OS's plus H's are gone, 8 IO3s plus 4 H2O, going to form 5 OSO4 plus 4 I2. The waters are gone, the hydrogens are gone, but I now have I gotta be careful. It's not 80 H minuses. It's plus 8 OH minus. And if you count all the atoms and ions and things there and charges, you'll see that it's balanced. So what I would say is balance under acidic conditions. So use the major hydroxide method, so that'll always get you to acidic, and then use the water reaction to convert to basic conditions. So I'm going to start with one more question. If you guys have hung on there this long, awesome. But I can understand if you gotta stop. Like, Dixon, stop talking, please. You're killing us. So let's balance. Let's balance this one here. MnO4 minus plus C2O4 2 minus going to form MnO2 plus CO2. Okay, and those chemicals there, we're going to balance this under basic conditions. So what that means is we would expect to see hydroxides when we're done here. So once again, I completely ignore that right now, and I just use the major hydroxide method to balance the 2 half cells, and then use the idea the electrons have to be the same, and then I use the water reaction to nullify it. So you can see this is a lot of steps. I mean, trying to remember all this just is a lot of processing. So once again, I know your time's tight, so I'm just going to do this for you, but please feel free to call out and say, Dixon, you're doing stupid things, okay? Because I do sometimes do that. So cell 1, cell 2, there's lots of stupid things I've done in my life, but chemistry things, here we go. So MnO4, and we're going to turn that into a chemical that has Mn. So the only chemical I see there is MnO2, so that seems to be most likely candidate. And then what am I going to do? I'm going to take the carbon compound, C2O4, 2 minus, and I'm going to turn that into CO2. Okay. So I'm going to now balance this under my acidic major hydroxide method here. So left-hand side, major species is Mn. There's 1 on both sides. I've got 4 oxygens and 2 oxygens. So let's add 2 more oxygens by adding 2 waters. I'm going to do it tight on the left-hand side here. So now I've added, oh my goodness, I've added 8 hydrogens. So I'm going to add 8 hydrogen. Oh, just squeak that in. And now my charge, once again, be careful here. I've got 8 from the hydrogens, minus 1 from the MnO4 minus, so really I have plus 7 here. And I have 0 on that side. So I'm going to need to add, oh, hang on, wait, sorry, what did I do there? 2H2O. Oh, sorry, back up. So you guys should help me out for that. So I have 4 hydrogens on the right-hand side. So 4 H pluses. And now I have a net charge of plus 3. Because I've got plus 4 from the hydrogen, but minus 1 from the MnO4. So I need to have 3 electrons being added here. Just try to squeak that in. That's pretty small. Okay, so that's definitely a reduction going on there. So for the other compound, I need to put a 2 in front of that to make 2 carbons. Now I now have 4 hydrogens on both sides, so that's good. And I have no hydrogens, 4 oxygens on both sides, no hydrogens, and a net charge of minus 2 on the left. So I'm going to have 2 electrons being added on that side. Okay, so now I've got 2 electrons being made and 3 electrons being consumed. So I need the lowest common multiple here, which would be 6. So I need to times this reaction by 3. and that would give me 3 C2O4 2 minus, going to form 6 CO2 plus 6 electrons. And then this reaction here, you need to times that by 2 because I need to have 6 electrons. So I'm going to get 6 electrons plus 8 hydrogens plus 2 MnO4 minus, going to form 2 MnO2 plus 4 H2O. And now when I add that, what I should notice, the electrons have to cancel here. So electrons are going to cancel. I've got 6 electrons on both sides. They're gone. And really no water and no hydrogen in the first reaction. So I can just basically go and finish this. So there's going to be 3 C2O4 2 minus plus 8 protons, which is why it's acidic, plus 2 MnO4 minus, going to form 6 CO2 plus 2 MnO2 plus 4 waters. Okay, now, so that's going to be 3, an 8, and a 2, and a 2, 4, and a 6. Yeah, there we go. Okay, so now I got to deal with the basic condition. So I've got hydrogens on the left-hand side, so I need them on the right-hand side. So I need to have 8 H pluses, so 8 OH minuses, so therefore 8 waters would have to be used. So I balance that out. I notice my hydrogens are now gone. So they're gone completely. I've got OHs now, which is basic. And waters, I've got kind of similar. Last one, I got 4 waters here and 4 waters left over there. So finally, I would have 3 C2O4, 2 minus, plus 2 MnO4 minus, plus 4 H2O, going to form 6 CO2 plus 2 MnO2 plus 8 OH minus. Super simple, right? Like pretty much like one step, right? So that is a horrendous task to balance these things. So once again, there is another method in the book. You can read about it if you want to use that. You're more than welcome to, but it's just one more method here. So I'm going to stop there, and I'm going to post this video. So if you didn't get all that written down, it'll be up there for you. And just before you guys sign off here, I just want to just talk about 2 quick things. Just stop that, stop sharing. And